We have here our normal curve. The only thing that's different about this curve is they have broken it down a little bit further. So instead of just -1, -2, 1, +2 standard deviations, they got the half deviations in there also. So all those percentages that we were talking about last time get broken down a little bit further. But 1 standard deviation below, 1 standard deviation above, that's still 68% of your data is going to fall there. 2 standard deviations below, 2 standard deviations above, that's still 95% of your data. And then 3 to 3 is still your 99.7%. But all they did is they broke it down a little bit further because you're not always going to get data points that fall 1 standard deviation above or 2 standard deviations below. You're going to get some that are going to be like 1.5, -2.5, that kind of thing. So when that's the case, we then use these percentages here instead. So let's take a look at our first example. We have the amount of soda in a standard can is normally distributed with a mean of 12 ounces and a standard deviation of 0.6 ounces. So if we have 250 soda cans were pulled from a company to check the volume, how many would be expected to have less than 11.1 ounces? So let's make our curve, just like we were doing last time. With our little line down below, that's our x-axis there. Right here in the middle is always our what? Mean, which in this case was 12 ounces. So we're going to put a nice little 12 there. 11.1 is going to fall to the left of my mean, so I'm going to start doing some subtraction. So 1 standard deviation below, if I take my 12, subtract my 0.6 from it, what would we get for that? 11.4. So 1 standard deviation below would be 11.4 ounces. So let's go to our 2. So subtract another 0.6. What do we get? 10.8. So where would 11.1 fall? It would fall in between these two, right? But exactly where in between them? Would it be exactly halfway between them? Yeah, because if you subtract 0.3, which is half of your standard deviation, you get to 11.1. From this one, if you add 0.3, which again is half of your standard deviation, you would get to 11.1. So this is at -1.5 standard deviations below the mean. So now in order to figure out how many soda cans are going to be less than that, if it's less than 11.1, it's going to be over here. We have to add up all of our percentages starting as far left as we can possibly go until we get to -1.5. So that means we're going to start with 0.1% for that part, plus our 0.5%, and then plus 1.7%, and plus the 4.4%, because that's when I get to my -1.5. So I'm not going to add up any other ones. So add those up and we'll figure out exactly what percentage is below 11.1. .7%. Now the question though is they want to know how many cans that is, so we just have to take the 250 soda cans and multiply it times our 6.7% as a decimal, so 0.067. We end up with 16.75, but can we have 0.75 of a soda can? So we say 16 cans. You don't want to round up to that 17 because that 0.25 is not part of it, so we round down to the 16. So let's take a look at the next one. We have a group of 625 students has a mean age of 15 15.8 years with a standard deviation of 0.6 years. The ages are normally distributed. How many students are younger than 17 and older than 14.9? Express your answer to the nearest student. So again, we'll start with our curve. Right in the middle of our curve is going to go what? 15.8. So again, we've got to figure out where on the curve is 17 years of age going to be and 14.9. So we're going to start some subtraction here. Our standard deviation is 0.6, so 15.8 minus 0.6 would give us what? 15.2. So minus 0.6 again would give us 14.6. So 14.9, would that fall equally between these two? Yes. So there's our 14.9. We found where that's going to fall. That's at negative 1.5 standard deviations. So now we have to find our 17, so we got to go up. So 15.8 plus 0.6, and then plus 0.6 again. There's our 17 over here at positive 2 standard deviations. So we're looking for all these percentages in between negative 1.5 and our positive 2. So if we look up above, we are adding the 9.2% plus the 15 plus 19.1 and then plus another 19.1 plus another 15 plus another 9.2 and then plus a 4.4. All of the percentages until you get to 2. What was it, Christine? 91%. So now to actually find the number of students, we just have to multiply. There's 625 times our 90.91. What do we get with our decimal? 568.75. Now, because this problem stated to round our answer to the nearest student, we don't do it like we did with the last one. That one was our implied rounding. This one they told us specifically to round to the nearest student. So it would be 569 students. You have your normal rounding rules when they specifically tell you where to round to. So then here it says, notice that the center is labeled 0 and the x-axis is labeled with your standard deviations. So our center right here is 0 standard deviations. That's your mean. Because what you have to remember is your standard deviation is how far you are from the mean. So if you're looking at the actual mean, your distance from the mean is 0. You haven't gone anywhere. So this is a standard normal curve. You're always comparing your data value to the mean. So you're always trying to figure out how far you are from that. So if you scored 1 standard deviation above the mean, regardless of what the mean is, you've beaten 84% of the test takers. So if you're taking a test, you've beaten 84% of the people. Your percentile rank would be the 84th percentile. Remember, that word percentile means it's comparing you to everybody who did less or worse than you did. So if we take a look at the next page, what ends up happening is there's different kinds of problems out there where you can't really compare your data. So like here, they want to know who was the greatest single season home run hitter of all time. And if you look at your data, we got Babe Ruth here, who had 60 home runs, but the mean of the year was 7.2 compared to everybody else, and the standard deviation was 9.7. But But then you look at Barry Bonds, who had 73, but that was in 2001, where Babe Ruth did that in 1927. So the numbers are different. Different things are happening. The way they train has changed. So it's not really fair to compare those kinds of numbers. So in order to compare your numbers when it's not exactly the same data set, we use what we call standardized scores, but we shorten it down to z-scores. So if I say z-score, this is what I'm referring to. Your z-score is your standard deviation. So therefore, your z-score tells you how far away from the mean you are. So the way we figure out our z-score is this little formula right down here. It's your value minus the mean divided by whatever the standard deviation is. So let's take a look at our numbers up here then. So for Babe Ruth, to figure out his z-score, it would be his value of 60, because he hit 60 home runs, minus the mean of 7.2, divided by the standard deviation of the time, which was 9.7. So go ahead, figure out what that is in your calculator. And we're going to round it to the nearest hundredth. Hundredth. 5.44. So that means he is 5.44 standard deviations above the mean. Do we even have that number on our chart? No. So that means he was pretty awesome for his time. So let's take a look next at Maris. Let's calculate his z-score. So his score of 61 minus the mean of 18.8 divided by the standard deviation of 13.4. So he had a z-score of 3.15. So between the two of them, who was better? Babe Ruth. Totally better. So what I want you to do right now is figure out what was McGuire's z-score, and then we'll have you figure out Barry Bonds' z-score. So now that we have our z-scores, now it's actually fair for us to be able to compare their data. So if we look at their z-scores, who was the better one?
Ruth.
Babe Ruth. Imagine if he had actually trained like we do today, how much he would be doing. It's like you read my mind.
It's like you read mine right here.
No, I didn't hear you.
There's an increasing trend between greatest of all time. They didn't like.
Yes. Amir did. All right, so if we have a z-score of 0, that means that is your mean value. As we were talking about, your standard deviation of 0 means you're at your mean. You're no distance from your mean because you're at it. A z-score of 1 means you are 1 standard deviation above the mean. So if it's positive, that means you're going to be above your mean. So a z-score of -2, what do you think that means? That means we're 2 standard deviations below the mean. If your z-score is negative, you're below your mean. So a few things for us to know about our z-scores. First off, you will always round them to the nearest hundredth. You're never going to round them to anything else. It's always going to be to the nearest hundredth. As we just said, a negative z-score is below the mean. Positive z-score means you're above the mean. An unusual value is a z-score of less than -2 or greater than +2. So what that ends up looking like, here's our curve. Here's -2. There's +2. So if you're beyond it here or beyond it there, you're considered to have an unusual value. So all 4 of our ball players up there, since they were beyond 2 standard deviations above the mean, all of their values were unusual. So then what z-scores allow us to do is it allows us to compare values measured on different scales. So for example, you can compare your SAT versus your ACT score then. And the larger the z-score, the better it is. So especially if you're looking at test grades, your larger z-score means you did better on the test than other people did. So let's take a look at our examples over here. So we have a boys heights in 7th grade are normally distributed with a mean of 62 and a standard deviation of 3.2. Find the z-score rounded to the nearest 100 for each of the following heights and show your calculation that leads to your answer. So as we just said on the last page, your z-score is your value minus your mean divided by your standard deviation. Yes. So then again, we're rounding to the nearest 100th. 1.25. So then for our other one over here, it would be 57 minus our mean divided by our standard deviation. That one should be a negative z-score. Negative 1.56. So in our second example there, we have Jeremiah took a standardized test with a mean score of 560 and a standard deviation of 45. If Jeremiah's score resulted in a z value of 1.84, then what was Jeremiah's score to the nearest whole number? So what we're going to do is we're still using the same formula, only this time we actually know what our z-score is. So instead of using the letter z, I'm going to put the score in there. So 1.84 equals. I'm looking for what his score is to be able to subtract the mean from. So I'm going to put x in for that. So x minus my mean of 560 divided by my standard deviation of 45. So we would want to multiply times 45 to get rid of it over there on the right side. So 45 times 1.84 would give us what? 82.8. And then what we would do? Add what? Add 560. So 82.8 plus 560. 642.8. Now they told us to round to the nearest whole number, so what would that round to? 43. So 643 was his score. He did. Yes. All right, so next part. What does that z-score actually tell you? So it tells you how far above or below you are from the mean. Using the standard normal curve, you can calculate what percent of the data you were higher or lower than. And that's where we get into our chart. So for example, number 1, the mean score on the math test was 70 with a standard deviation of 5. If you scored a 75, what is your z-score? So let's have you go ahead and figure out what your z-score was. You should get a 1. So that one gives us a z-score of 1. So a z-score of 1, we've dealt with this before. If we have our little curve, here's our mean of 70, here's our standard deviation of 1. To figure out what percentage of students you did better than, we would add it. 50% to get you to your mean, plus another 34% to get you to that first standard deviation. What percent of students did you do better than? 84%. All right, so that one was easy because standard deviation of 1, we've been dealing with that. What if your score was a 77 though? So let's figure out our z-score if we got a 77. 1.4. Was that ever on our little curve that we've dealt with? 1.4? No, we started with 1.5. But would that help us with a 1.4 z-score? No. So that is why you have that chart that I've given you. So let's take a look at this. I have just a little snippet. You guys have the full chart on your paper. So a z-score of 1.4. With our z-score, your tenths are in the columns that are going down. And then your hundredths are going across the top. So we just had a z-score of 1.4, and then I'll put the 0 in there to make it to the hundredth. Like I told you, our z-scores are always supposed to go to the 100. So we would go down here to 1.4, and then over to the 0 for my hundredths, and I get that number off the chart, 0.9192. So what that means is if I turn this into a percent, that means I did better than 91.92% of the people on that test. So it gives you the same answer as what you would have gotten for your curve. You just have to look to the chart for it. And it goes the other way. So like for example, my number I have circled here, my 0.6950, what would that be as a percent? 69.5%. Its corresponding z-score would be 0.5 and then 1. So that's the z-score that goes with it.
So these are like the z-score with the column going down is the z-score.
Well, all of it's a z-score. The column going down gives you to your tenths place. Across here gives you to the hundredths place. So then you have to match the two of them together to find your score. So let's take a look at some examples. Practice using our chart there. So the average weight of a full-grown beef cow is 1,470 pounds with a standard deviation of 230 pounds. If the weights are normally distributed, what is the percentile rank of a cow that weighs 1,750 pounds? So in order to figure this out, first thing we have to do is figure out what is our z-score. So that's our value minus the mean divided by the standard deviation. So 1,750 minus 1,470 divided by 230. Yes. So to the nearest hundredth, we get a z-score of 1.22. So on your chart, you're going to go down until you get to 1.2, and then across until you get to 0.02, and find your decimal off the chart. That corresponds to your 1.22 z-score. Which if you did it correctly, you should have gotten 0.8888. So 0.8888 as a percentage is what? 88.88%. But we never use decimals for our percentile rank. So what would our actual percentile rank be? 89th percentile. So that would be the rank for that cow. So the z-score also can determine your probability. If I didn't take this number here and turn it into a percent, that number is my probability of getting a cow that weight or less. So you have to be careful of the wording of a question, because sometimes they ask you for a percent, sometimes they ask you for a percentile, sometimes they ask you for a probability. So you got to make sure you know which one they're asking you for. So a lot of times what helps make it easier is actually kind of sketching a picture of what it is that you're trying to look for. And then there's other times you don't have an option. They tell you you have to sketch the picture. So we're going to practice it. So we have here, if the scores in a standardized test are evenly distributed or normally distributed with a mean of 560 and a standard deviation of 75, answer the following questions by using z-scores and that table that I've given to you. So first one, we're going to find the probability that a test picked at random would have a score less than 500. So let's first draw our picture. So we're going to start with our mean right in the middle, 560. Our standard deviation is 75. So what would one standard deviation below be equal to? 560 minus our 75. What do we get? 485. So can we agree that 500 would fall between those two? Yeah. So we're just going to kind of estimate. 500 would be approximately there. I put my number up on the top because they're all pretty close together under there. So we're looking for who scored less than 500. So we're looking for the percentile ranking, basically, of who scored less than 500. So what we're going to do is we're going to first calculate our z-score. So your score minus your mean divided by your standard deviation. So what does that give us as a z-score? Yep. So negative 0.80. I only put the 0 there to help me with my table to remind me I'm going to go to the hundredths column of a 0. So then to find the probability, we have to now go to our chart. So you're going to go to negative 0.80 for a z-score and get your number off the chart there. You should get 0.2119. So that right there, this chart always gives you how many people did less than that score. So it's always cumulative starting from the left. So that number right there, that is the probability of getting a score less than 500. I went on my z-score chart to negative 0.80, and that's the number I got. So now B, find the probability of getting a test of 720 or less. So we're going to do the same thing. First, put my mean on there, 560. 720 is higher than that, so I'm going to add my standard deviation. What would be one standard deviation above? 635. Not quite there yet, so let's add another 75 to that. What do we get? 710. So 720 would be where? Wouldn't it be just beyond my 710? Yeah, so my 720 is approximately there. And we're looking for 720 or less. So just based on my shading, our probability should be what? A pretty big number, right? So let's calculate our z-score first. So our value minus our mean divided by our standard deviation. So what do we get as our z-score?
2.1333333.
So 2.13. Remember, z-score is always to the nearest hundredth. So then look on your chart to 2.13, and that'll be our probability of getting a 720 or less. 0.9834. So now the next one, C, tells us find the probability that a test picked at random would have a score larger than 720. So there's my mean. I'm going to go put 720 on my curve, just like we did on the last one. But if we're trying to get a score larger than 720, which way should I shade this time? To the right. So we've already figured out this z-score. That was 2.13. We have also already figured out the probability of scoring less than a 720. So to score higher than a 720, you would take 1 and subtract that number from it that was on the chart there. So if they want higher, it's always 1 minus the number from the chart. In which this case would be what? Oh, I missed my 0. 0.0166. So is it very likely you're going to score higher than a 720? No. All right, so then our last one, find the probability that a test picked at random would have a score between 500 and 600. So again, there's my mean, 560. One standard deviation below was 485. One above was 635. We've already figured out those numbers. So 500 is going to fall in between those two, 485 and 560. 600 is going to fall between 560 and 635. So we're looking for the score in between them. What's that probability in between those two numbers? So now we've already figured out our z-score for 500. For 500, our z-score was negative 0.80. And the probability of scoring less than a 500 was 0.2119. We've already figured that out. So we need to figure out our numbers for 600 now, though. So we'll start with our z-score. 600 minus our mean of 560 divided by 75. Which would give us a z-score of 0.53. So look on your chart for your 0.5, where it meets your 0.03. 0.7019. So now to get the percentage in between the two, you just need to subtract it. So 0.7019 minus 0.2119. So the probability of getting between a 500 and a 600 is 0.49.